Hello everybody and welcome to Thermal Physics Lesson 6. Now in the last video, and really sort of stretching back even to Thermal Physics video 4, we were looking at the ideal gas law, and we've got two slightly different versions of it. We've got PV is equal to nRT and we've got PV is equal to nKBT. Now, at least from the main variable point of view, we've got P times V is proportional to T in both of them, so pressure times volume is proportional to temperature. In both versions, we're just messing around really with this middle bit. Firstly, looking at the measure of how much gas we've got. So, little n is number of moles, whereas capital N is number of molecules. And what that gives us then is two ever so slightly different constants. R, the ideal gas constant, being 8.31 joules per mole per Kelvin. Whereas in the other version we've got Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. Now in this video, and going on to the next video as well, we're going to have a look at the kinetic theory of gases. Now this, I will sort of warn you now, is going to be quite theory heavy. We are going to do what is going to look on the face of it like quite a big derivation to get to our final destination. What I will say, just a little bit of a health warning, is that you don't need to know off by heart every single little detail, especially when we get into the derivation. But there are certain bits that you will need to know and you will need to understand. You will need to obviously know off by heart, and I'll try and highlight those bits as we go along. What you need though is an understanding of the process that we're taking. Now in this first video we're going to really do a lot of the setting up, and we'll do most of the derivation itself in the next video. Firstly then, I want to have a look at molecular speeds. And the first thing that I want you to have a think about is this. Firstly, if we were to draw a graph of sort of molecular speed, molecular velocity, as a frequency distribution. So before I very simply draw this, what I want you to do is think about this yourself. Now, if we were to take a gas, and we were to have a look and we were to measure the velocity of every single molecule in that gas, and we were to plot a graph of that velocity, obviously on the x-axis, and the number of molecules that we've got at a particular velocity on the y-axis. Okay, so we're not necessarily talking about frequency here in the same way that we're going to look at frequency when it comes to waves. Really, this is a frequency distribution, very similar to what we look at when we look at the maths and when we're looking at especially the statistics side of maths. So maybe just have a quick think, what's this graph going to look like if we could measure the velocity of every single molecule and draw that frequency curve? What's it going to look like? Well, I'm going to sketch it on and then we'll obviously explain it. What it's going to look like is something along these lines. Okay. So firstly, we've got a few different things. You might look at this and think to yourself straight away, especially if you've done a lot of statistics in maths, you might look at it and think that this looks very much like a normal distribution. Now you wouldn't be far off. It does look kind of like a normal distribution, but it's not quite a normal distribution. There are a couple of subtle differences which we'll try and talk about in a moment. Now, what we've got then is that as we increase the velocity, we get obviously more and more molecules moving at a certain velocity. You'll notice that there are no molecules with a velocity of 0. Secondly, you'll notice that we do have a tail on the right hand side. Okay, now what that means is that we've got two different things we can look at. Firstly, at this point here, we will have the most probable molecular speed, but where the average speed would be slightly higher than that. Because this distribution isn't symmetrical about that most probable speeds. Okay, so we do have a little bit of a tail on the right hand side, which just brings the average speed slightly higher. Now, the technical name for this kind of distribution is called a Maxwell-Boltzmann distribution. And you'll notice that we've got that name Boltzmann cropping up again, and of course it's the same Boltzmann after whom the constant is named. So when I said in the last video that we're going to come across Boltzmann's constant again, you can see that Boltzmann obviously did quite a lot of work looking at kinetic theory, and therefore that's why we see his work cropping up in more than one area. Now, the next thing to think about with a Maxwell-Boltzmann distribution is what happens if we take the gas and we either increase or decrease the temperature. Now, we know the rough idea that temperature and kinetic energy are linked, so therefore with a higher temperature we expect a higher kinetic energy, and therefore we expect, at least on average, a higher velocity as well. What's going to happen to the graph then if we increase the temperature is we're going to end up with a graph that looks something like that. Now, you'll notice that two things have happened, and what we're going to do is we're going to focus on the peak of the graph. Now, the peak of the graph, okay, is there. And two things have happened to the peak. Firstly, we can see that the peak has moved to the right. Now, of course, it's moved to the right very simply because the molecules now have a higher speed. You'll also note, though, that the peak is lower. The reason why the peak is lower, we need to think about what the area underneath this graph represents. Well, of course, this is a frequency curve, and if we were to have a look at and go way back and understand exactly what a frequency curve means, if we were to look at the area under the graph, in other words, if we were to assign a point to everywhere underneath that graph, that would give us the number of molecules. Now, therefore, that area has to remain a constant. Okay, so the area remains constant, okay, because the number of molecules also has to remain constant, because that's what that area, bearing in mind that we're talking about a frequency curve here, that's exactly what that area represents. Now, obviously, if we go the other way and we look at decreasing the temperature, what we're going to end up with is the exact opposite. we're going to end up with a higher peak and a peak that has moved to the left. Okay, so lower temperature would give us a lower kinetic energy, and that would give us lower molecular speeds. Okay, so the peak has moved to the left because of obviously those lower speeds, and then, as we said, the peak will move up. Okay, because we still need to keep the area under the graph as a constant. Now, when it comes to the Maxwell-Boltzmann distribution, it's not very convenient for us to use a simple arithmetic mean to find some kind of indicative value, to find some mean value for these velocities. It's far better mathematically for us to look at what's known as the RMS. Now, the reason why that is, I'm not necessarily going to get into now. What we're going to have a look at, though, is this idea of RMS. Now, RMS you may have come across before, especially depending on how far you've got through with electricity. If you looked at alternating current electricity, at least to an A-level standard, you'll have come across RMS in that. If not, don't worry, because we're going to explain it anyway. Now, RMS stands for root mean square. And what we do in order to calculate RMS is we work backwards through those words. So in other words, if we've got a set of values, we're going to square them first, then we're going to take the mean, and then we're going to take the square root. So in other words, if we've got a load of different speeds, V1, V2, V3, V4, etc., up to Vn, where n, of course, represents the number of molecules. Then in order to calculate the RMS, well, we're going to work backwards again. So we're going to square them all first. So we're going to do V1 squared, V2 squared, V3 squared, all the way up to Vn squared. So we squared all those numbers. Next, we're going to take the mean. So we're going to add them all together. And of course, to take the mean, we're going to divide by the number that we've got. So we're going to divide by n, the number of molecules. And then finally, we're going to take the square root. Now, you may be thinking, well, what's the point of doing that? And what we'll do is we'll move over to a new slide, and we'll work through with a relatively simple example, and I'll show you really where the idea of RMS comes into its own. So let's have a look at how we calculate RMS using some numbers. Now, obviously, these numbers I've just made up, but hopefully this will give us the right idea. Now, you can see here straight away that I've got a couple of positive numbers and I've got some negative numbers. Now, what I want you to do, just very quickly pause the video and work out, calculate what just a straight arithmetic mean for those 5 values is going to be. So hopefully what your calculator has told you once you've worked all of that out is that the mean, and obviously we normally use that bar notation, the mean of all those numbers is minus 0.2. Now, when we think about that as a number, that really doesn't represent what we're trying to look at here. If we look at the magnitudes range from 5 to 12. So therefore, having a mean value of minus 0.2 doesn't represent this distribution in any way, shape or form. What we can do then is we can calculate the RMS. So the first stage, of course, is to square all of those values. And again, might be worth, again, just pausing the video and following me through on this. So 8 squared is easy, 64. Now minus 7, don't forget when we square it, multiply it by itself, and a minus times a minus is always a plus. So it ends up as plus 49, we've got 144, we've got positive 25, and we've got positive 81. So you can see straight away that one of the advantages of using RMS is that it gets rid of any negative signs that we've got, and I'll explain in just a moment time why we might want to do that, especially when we're looking at kinetic theory. Now, of course, the next stage, so we've squared everything. The next stage is that we need to take the mean. So again, just pause the video and calculate the mean of those 5 numbers. And what I get is that the mean of v squared is equal to 72.6. Now again, the final step, as we said, is we've got to take the square root. So what we end up with then is that the RMS of those 5 numbers is 8.52. Now suddenly, by doing the RMS, we've now got a much better representative value of those 5 numbers on the right hand side. In fact, if we were to take those 5 numbers and just take the magnitude, in other words, get rid of all those negative signs and do the mean of those 5 numbers, then what we end up with is 8.2. And again, if you just want to pause the video and just verify that yourself, then please do, and just make sure that you get the same. Now, obviously, we need to think about the advantages of doing RMS. Well, firstly, from a statistical point of view, we've got 2 different ways of looking at it. We've got the RMS 8.52 for that set of values, and obviously we know that if we just knocked the minus signs off, we'd have got a mean of 8.2. Now, from a statistical point of view, as our sample increases, those 2 ideas will get closer and closer together. So the RMS and the mean of the magnitudes will get closer and closer together. But of course, from a physics point of view, where RMS really gives us an advantage is it gets rid of any negative signs. And in a way, when we're looking at a gas where we know that molecules are moving in all directions in 3 dimensions, and if we treat it properly, well, a molecule moving to the left will have a negative velocity, and a particle moving to the right will have a positive velocity. And if you were to do the mean of all those, you'd probably end up getting pretty close to 0. So the RMS really has the advantage of giving us that sort of indicative value without taking into account the direction, which of course, hopefully, if you can start to see where things may be going, you can see that especially when it feeds into energy, that's going to have a massive advantage for us. Finally then, before we move on from RMS, hopefully we can see very simply that as the temperature of a gas increases, then that RMS velocity will also increase as well. Next then, almost the last thing that we're going to do in this video is we're going to have a look at the assumptions that we make in kinetic theory. Now, as you can see, there are 5 of them, and these 5 do have to be memorised. It could be a very sort of simple exam question just to recite maybe 2 or 3 of these assumptions for maybe a 2 or 3 mark question. Now what we'll do is we'll work through and we'll sort of justify them in our minds as we go along. So firstly, the first assumption is that molecules are treated as point objects. Now what we mean by point objects is that the volume of an individual molecule is definitely orders of magnitude less than the volume of the gas overall. Now, I think that's fair enough. Even if you take a relatively small volume of gas by our standards, the molecules are a lot smaller than that, and therefore we can just take their volume as negligible. Now, the second one, there are no forces acting between the molecules. Well, yes, okay, there might be a tiny little bit of gravitational attraction between them, but again, because their masses are so small, then that again can be negated. And of course, from an electrostatic point of view, molecules should, in theory, be neutral overall, so we're not going to get any attraction or repulsion there either. Now, the third one, molecules moving in Brownian motion. Hopefully we remember that phrase from GCSE. What Brownian motion means is it is a random motion. So in other words, if we were to track an individual molecule, then its path will go all over the place like this, because of course as it's moving, it's being collided with by other molecules all the time. So it's random motion, and that is due to intermolecular collisions. Next one then, all collisions are elastic. Well, again, remember back to year one. Remember what elastic means. Elastic means that no kinetic energy is lost in the collisions. And then finally, collisions take a negligible time compared with the time between successive collisions. Again, this partly comes down to the fact that the molecules are so far spread in a gas that the time they actually spend colliding with each other and making each other change path is so small, so negligible, compared to how long it takes them to go on and have a new collision, that again it can be treated as negligible, and therefore for the main bit of the theory we can ignore it. Finally then, for this video, we're just going to have a very quick look at velocity in 3 dimensions. Now, we're used to this in 2 dimensions, and to move up to velocity in 3 dimensions isn't going to take that much brain power, that much extra learning to do. Now, if we have just a molecule in a gas in a box, and we're going to label our directions as X, Y and Z, therefore our molecule has got velocity in 3 dimensions. We've got Vx, we've got Vy, and we'll have Vz as well. Now, of course, we know that in 2 dimensions if we have velocity in 2 dimensions, then in order to work out the total velocity, we just apply Pythagoras theorem, so it's just Vx squared plus Vy squared, and then square rooted. Now, in 3 dimensions, it's almost exactly the same approach. We just take the square root of all 3 squared instead. So to summarise then, in this video we've done a lot of the setting up required to really dive into kinetic theory in the next video, and obviously a lot of those things in the next video you won't understand unless you've done the background in this video. So while, as I know, it is very theoretical heavy, it is definitely worthwhile getting it all set up. Maxwell-Boltzmann distribution was the first thing we looked at then, and Maxwell distribution is a frequency curve of velocities in a gas, and it looks like that, similar to a normal distribution but with subtle differences. Now obviously we said that as the gas gets hotter, that peak is going to move down and to the right, and as it gets cooler it's going to move up and to the left. And remember that the area underneath that graph is equal to the number of molecules. Secondly then, we looked at the RMS velocity, and remember that RMS stands for root mean square. And in order to calculate root mean square, we just work backwards through those words. So firstly, we square everything up to however many we've got. Then we take the mean, so we add them all together and divide by however many we've got. And then we take, finally, the square root. And then the last thing we looked at was 3D velocity. So if you've got components in 3 dimensions rather than just components in 2 dimensions, and the total velocity is the square root of the square of each of those components. So that's it for this video. As usual, thanks very much for watching, and I'll see you in the next one.